Okay, so welcome back to the last session of the first Flux introduction training of this year. So this is the last day. Can you hear me? Great, thank you so much for the feedback. So today we will hand the thermal and the MVH, and we will start the MVH analysis with FluxMotor, and then we will see how to optimize and how to export the model and the behavior of the machine for the lookup table. So yesterday we stopped the exercise here. So we seen just the pure thermal analysis, and we had the electromagnetic analysis. So let me open FluxMotor. As always, we have to go to the motor catalog. Okay, now from here, we have Flux Training, our folder. We need to take the exercise that we stopped yesterday and edit. So the model will appear, and just a moment. Okay, so sorry. Let me take the FluxMotor model here. Okay, so yesterday we performed the steady state analysis and the transient one. Just a pure thermal. We have two saved tests that we saved in the first exercise, and today we want to see the effects of motor temperature on the electromagnetic performance. These effects can be included on several tests on FluxMotor through the thermal settings. We have the possibility to include the characterization, the model test here. Just a moment. So it is possible to perform thermal solving to consider the impact of the magnet's temperature in a predefined range of temperature. The results includes a different set of maps for different temperature. Then we have the working points in wave. So we can enable the thermal solving and choose either iterative process in this case. So to reach the convergence between EM and thermal, or a single iteration process to perform electromagnetic computation coupled to thermal analysis. And so the results will include final temperature charts and table and their effects on the electromagnetic performance in the working point. But we also have the possibility to include the thermal solving with iterative process, so to reach the convergence, to perform electromagnetic computation coupled with thermal analysis for the performance mapping in sine wave. So here, in the result, it is possible to check the final temperature for a specific working point, or the temperature rise versus time for a defined duty cycle. So let's see how to do this type of first of all, we need to go to the characterization model here, and now we need to repeat the steps that we did in the electromagnetic part, but this time what is changed is here in the thermal. We can avoid to set fixed temperature, and we can click on, as you can see here, thermal solving yes. So this time we can leave the temperature like FluxMotor suggested, just the magnet maximum temperature need to be changed. So we can set one and 4 like as a number of computation for magnet temperature range. Okay, the other temperature just start. So okay, about okay, let me just quickly take okay. So about the electronics, we can leave the data we have here that we entered yesterday. So my efficiency 98 and the rated power of 120 kilowatts. And about the mechanics, the same. So 6,200 for the reference speed, for 150 for the losses at reference speed, and 0.35 for the coefficients. Okay, about the test, the other things on the test, we want to set, yeah, line current is already set to 250, and the maximum speed is 15 per pm. So we can just click on OK and apply and start the test. So at the end of the computation, all the maps will be temperature dependent. So we can see the same results that we seen yesterday, but yeah, this yeah, we'll have also the temperature. So maps for each temperature. So in the meantime, what I shared today is the last chapter about export and optimization. And yeah, I will try to run a bit to be able to see all the things today. Just a few minutes. In general, we can see that, just to recap, for the thermal electromagnetic thermal solving, we can consider the temperature, I mean losses that create the increasing temperatures in the motor. In the characterization model, as we've seen in the thermal icon is possible to set the couple analysis, the working points in wave, and in the performance mapping. In the meantime, let me. Okay, for the next exercise, we will need hyper study. I hope you you already have this tool on your machine. The license is the same of Flux and FluxMotor, so no problem to use it. You have just to download it from our site and then yeah, use it. You will see that it's very easy to use. And just 2 words on hyperstudy. In the meantime, it's a very powerful tool that can works with Altair's tool and not Altair tool. I mean, also solvers from competitors, but you can use, for example, Python scripts, Excel files, and so on. So it's very powerful. You can couple multiple physics. So that means that you can have in the same hyperstudy model, flux motor model, a thermal model made with an equivalent network. For the moment, you can create it with the twin activator or PSIM, but the thermal equivalent network made by FluxMotor will be exportable and available soon along this year. So, and you can also couple the Flux model or for advanced studies, or for example, OptiStrat model to carry out a specific analysis on mechanics, the MVH. Also, SimLab can be coupled with hyperstudy, so it's quite useful. Okay, I mean, if you have some doubts, please share them by the end of the session because it's the last day, or you can contact me. I put my mail address in chat. Otherwise, you can just open a support ticket and me or one of my colleagues will reply and will help you. This time takes more time than yesterday, for sure. We included the temperature analysis, so the thermal analysis. Okay, probably we can skip the solving time for this test just to be in time and to have enough time to see the next chapter. Let me see. Okay, we can no, let's wait a bit. Okay, I can show you the results from another model just to speed up the process. So this is the same model, but is solved for the characterization model. So now we can see the same results we had last time. I mean yesterday. Okay. Let me check. Okay, so yes, we can go. We can see the same results, but with different values, due to the fact that we included the temperature here, and in fact, if we go then to the losses, starting with the stator iron losses, you have the possibility to change the map depending on the speed and depending on the temperature of the magnets. So this is how, I mean, the results can change. The same for the power electronic losses and the total losses for sure, since it's the sum of the losses we have. Also for the axis flux linkage, we have the possibility to consider the temperature, and the mechanical losses are fixed because we set them. So okay, we can continue. Sorry. We can continue with the sine wave test. Here, so with, for the working point, we can click on thermal and considering an iterative solving. So for the model, it was just one iteration solving. So we can see the effects of the temperatures on the machine. In this case, we can consider instead the real temperature in the working point. So the process is an iterative one, and we can start at 50 degrees or leave the previous temperature is the same. I mean, probably a FluxMotor needs more time if you are quite distant from the real temperature, but you can leave the previous temperature for sure. But click on iterative solving. Okay, about the electronics and the mechanics. We have the same, so we can consider circle, loss computation, yes, and 1.25 here. And about the mechanics, okay, is already set. So the computation will be fast for this time. Okay, let me just put no about the ripple torque analysis. We are not interested in it. And let me start the test. This time will take less time because it is just one working point. It's not a model maps. And in addition to the electromagnetic results, the temperature charts and tables will be included this time. And we expected a bit of, I mean, some different results from the previous exercise, just with only electromagnetics stuff. Because I mean, all the materials set by default that you can use from the FluxMotor library are temperature dependent. So we can see some different results. Not so much, but some differences can be seen. Just a few minutes. Okay, so the test is ends. And now we can see a new part with the, as you can see here, the ISO values, but the temperatures. So we can see the radial temperatures. We have the graph in radial view and in the axial view. So we can see also the temperatures on the end winding, on the bearings, and on the shaft. And we have also the table with all the temperature for each parts of the machine. About the performance, as you can see, the mechanical torque is slightly different, so is decreased a bit, such as the maximum efficiency, if I remember well, for the same working point. So the last possibility we have in FluxMotor to take into account the thermal aspects, so the thermal solver, is the performance mappings in wave. Also this time the thermal solving is iterative, so you have just to put you have just to put some temperature here, or you can leave the temperature we have, and set the electronics and mechanics if you are interested in it, as well as the possibility to set the duty cycle like we did yesterday. You can add it also later in a second moment, since you know, it's a posteriori computation. So just apply inputs and play the test, start the test. I don't want to lose time to wait for the results, so I leave to you the possibility to do it and check the results. But some of the results are the temperature rise versus time for the duty cycle also. And yeah, you will see all the parts, the temperature for all the parts along the time, and so on. So let's continue with the MVH working point. For the working point analysis, and the purpose of this test is to perform MVH analysis of the machine when operating at a targeted working point to find the current magnitude, control angle, and speed. So this test gives data allowing MVH prediction in early electromagnetic and design stage. So it's quite powerful. This time we need to click here in the mechanics icon section. We have the MVH test. As you can see here, we have current, control angle, and speed. So the inputs are, again, the line current, the control angle, that is 37, as we used before, and again, the working point is 4,000. As a speed of, sorry, 4,000 RPM. About the other parameter here, we want to see the forces on it, so we need to put yes. The other things can be remained, the other parameters can be remained as suggested. Okay, so it's fine. Apply. And we can start the test. So about the max engine order, the max engine order is when decomposing the Maxwell pressure applied on the stator to get its harmonic contribution. So the max engine order, or a maximum engine order, is required to compute its decomposition in function of the time. We also have the number of computation to pitch here, and that allows to choose the number of Maxwell pressure evaluation per tooth. So it depends on the width of the tooth, but more Maxwell pressure evaluation we have on the tooth, more accurate FluxMotor can be. So the more the max mode spatial order instead here allows the user to define the number of modes to be considered for the acoustic structural analysis. And if the user selects 25, it means that the highest number of lobes in the stator deformation will be equal to 25 lobes. So it's a quite good number. In our case, it's 20. But it's enough for our exercise just to see what are the results, how to set the computation, and what are the results of the analysis. I remember you that you can click on the help here, so on the question mark, to check and to have more information about the test and the settings and the results of each test. If you need more information about NVH, for example, since in this FluxMotor introduction training, we don't have a lot of things. So the NVH results here shows the model analysis, the number of lobes we set. I just told where we can set it, and we choose 20, so we can see the number of lobes, the maximum number of lobes, depending on the frequency, on the natural frequency. We have the radiation efficiency here, so the acoustic radiation factor, depending on the frequency. We can just select one of this curve or see all together. The normal flux density in the air gap in space-time area. Also, we have rotor position and mechanical angle. The Maxwell pressure in the air gap in space-time area that has more or less the same shape, let me say, of the previous map. And we have here instead the Maxwell pressure. Then we have the Maxwell pressure polar plot against rotor position and space-time harmonics analysis, so is the FFT. We can change the position of the rotor and see how the polar plot can run or rotate. And the Maxwell pressure here, the space-time harmonic. And here we can decide to have the frequency or the engine order. Again, engine order versus spatial order, we can check the sound power level. Engine order and frequency, you can normally change the x-axis. We also have the sound power level versus engine order or frequency. And the magnetic forces on teeth versus rotor angular position. So also here we can rotate the rotor and check how the forces can change and rotate with the rotor, so with the magnets. Okay, so we also have the possibility to do the spectrogram analysis here. And the purpose of this test is to perform NVH analysis on the machine when operating at a set of targeted working points. So this point can be defined by the user through a set of current, magnitude, control angle, and speed, or through a set of torque and speed operating points. So can be defined automatically to follow torque speed envelope. So let me choose this time. You can set the values here, and clicking on the question mark, you will see what is how is made the predefined Excel sheet that you can consider. Otherwise, you can click just on torque and speed to set up the torque speed envelope. And now we can leave auto here. We need to adjust the line current, that is 250. About the voltage, we can put 265, or we can, as we did yesterday, set up the electronics and put the DC bus voltage here, but this time we neglect it. So we need to put the voltage value. The command modes and the maximum speed here, 15,000. Let me just check the other parameters. 20. Okay. Okay, I think it's fine. We can just apply and run the computation. Since the MVH is not a pure finite element based computation, it will take less time than the other maps outputs. The results are quite similar to the sine wave test, I mean, to the working point test that we did just now. But this time we have multiple speed and torque values. Can you hear me? Okay. So here in this test, I'm not sure if I was muted or not before. So just some limitation. I want to give you just some information about the limitation that we have, especially about the ratio between the L frame and the L stack. So the length of the frame and the length of the stack that has to be lower or equal to 1.5 for your machine. Otherwise, the analytical approach that we are using within FluxMotor can give you not so accurate results. I already shared the presentation. The presentation for today is about optimization, and we are going to do it together, but you can find the link in the chat at the beginning of the history. I can put again the link if you need. Okay. So today we seen in the first hour how to set up electromagnetic and thermal coupled with thermal analysis. Just to recap, the thermal analysis within FluxMotor is made with an equivalent thermal circuit that will be available soon for the export. For the moment, it's not visible, so you can't change it and you can check it. The coupled computation is available for the model maps here, for the scene wave working point, and for the performance mapping scene wave. So now we are performing the spectrogram for the MVH analysis to be able to check the MVH performances of the machine in multiple working points. So we are considering a torque speed envelope. We choose the auto, but you can set it, or you can also use current control angle and speed and use a table so to define the working points to consider. Okay, probably this could be also the reason. It should be line current 250. Not sure why this is not changed, but no problem. It's just an exercise. So in the meantime, let me take the last chapter. Okay, so the last chapter is about FluxMotor optimization and export within FluxMotor. So the material I shared with you, it's mainly dedicated to the optimization. I changed a bit of the content of this chapter. But we will see also some, let me say, how to export other document, for example, or advanced tools. So the model for couple FluxMotor with other tools. So I will show you in real time. So the export area has three main families of functions. The first one is the document. We can export the script, so build and export a Python script of a current motor in the application script factory or in a targeted folder. Script Factory is available from the supervisor of FluxMotor and is the tool that allows you to script and to command FluxMotor via script. And exporting the script, you are able to rerun it and change some function to do your scripting. The report, there is the possibility to generate reports in PDF or HTML format for all information about the model, including the selected design, the test area, so you can select just one test or all the tests that you did, including the thermal one. And also the winding scheme can be plotted in a PDF document to be able to share the architecture of your winding. For the advanced tools, we have, first of all, HyperStudy, that is the optimization tool that we are going to use to optimize and to perform DOE of our project. In the advanced tools, we also have the possibility to export the model for Flux. So we can export the 2D model, the SKU model, or the Flux 3D model. Just pay attention because for the 3D model, normally we need to, let me say, adjust the mesh normally for a specific computation, especially for the cognitive torque analysis. The last family is the family about system analysis. And here we can export files in FMU or MAT format to be used on system or circuit simulation tools like Altair Twin Activate or PSIM, but also with other competitors. Okay, so I propose to do the break, the coffee break, just 5 minutes, so we can restart later with the optimization stuff and the export one. So I hope the test will end. Otherwise, I will leave you the possibility to see the results and I mean, check the results and compare the results with the previous test. And yeah, I mean, okay, great. The test is end. As I told, this is wrong. I mean, we need to add a line current of 2050, but it's not a problem. So we have IMAG results here. Okay, and we have 3 different methods that are compared. We have the mechanical torque versus speed with the base point, the power versus speed. Also here we have machine electrical and mechanical, the current line versus speed, the control angle, so on. So the previous, the same results that we had before, but going into MVH results, we have the model analysis, the radiation efficiency, and the sound power here. So the radiated sound power spectrogram in speed engine order area. So this is quite powerful. We can see the level of the sound power and where the sound power is higher. The sound power level spectrogram in speed frequency area this time. We have the same level for the sound power. The sound power level per engine order versus speed. The overall sound power level versus speed. Okay. So we can take a break. and 5 minutes of break, and then we can start directly with the optimization process. Okay, so we can restart. Just wait a few minutes for the people. We already seen the overview. So the motor is the same that we handled along these 3 days. Is a very similar to the Nissan motor. So just some problem description here. Okay, what we need to do is to take the model that we created yesterday. Sorry, that we created the first day. So the electromagnetic, the first model that we created. And to do it, we need to go in the motor catalog here and choose, sorry, and choose the EPHAM 80 kilowatts day one. So we can save it. We can edit it and sorry, what we can do. Okay, here is to the model. Okay, and change the name. So it's not day one, it's day 3 or optimization. You can name model as you want. Okay, when it appears, we can edit it to open the model and to start to work for the optimization process. So the objective here is to minimize the torque ripple and magnet weight as a specific working point for the baseline design. That is the 4,000 RPM, 250 ampere ms, and 37 as control angle. So the optimization will be focused on changing the magnet shape only. It is just an example. Keep the mechanical torque higher than 193. We started from the 195. And the baseline, I mean, the magnet parameters and the baseline is this one. So we can see finally the export section. And here, before going into the optimization process, I want to show you the report that is very powerful. So we can export the PDF. Here we can choose the test, check which test we have, and export from here the test available. So as you can see, we have a lot of tests available. We want to, for example, export the results of the open circuit tests and also the working points in wave. We are interested in the material and yeah, we can click on all to export all the tests that we did. We can click on apply and have a preview directly inside FluxMotor. Then we can export it using this button, and we can see the machine, our machine, the winding scheme, some structural data and general data, the final parts, rotor part, with some parameters related to the part that we will use along during the optimization. If there is skew or not is included, it can be included. The stator shape and the parameters of this part. The skew is not there. The characteristics, the material, the slot filling here. I remember that in the first day we didn't use potting and liner for the slot. So, but if you set it and you export all the stuff, you will see for sure all the things. Then the radial view of the winding scheme that can be quite clear. The spatial representation. So all the data are available in the PDF, as well as the cogging torque versus rotor angular position, as well as the results. So we also the back MF, and we also asked the flux in the air gap and the ISO lines, or I mean the ISO values, the torque and the harmonic analysis on the torque relative to the working point analysis, and so on. We have the possibility to export the script, as we've seen before. Also for the system analysis, we have the possibility to export the lookup table. You can import the task configuration. Here we have it. So you can use previous model maps here, test to export the lookup table, and we can import the inputs from here. And at the end, we have different possibilities. We can export the FMU to inactivate for a generic, a generic FMU for to couple it, to use it with other non-Altair tools. And this one, that is the MatPCM Activate, that is the most used one. And the destination folder. Click on apply inputs and export the model. Unfortunately, along this during this training, we will not see the system analysis, but yeah, this is what we can do. About the export of a Flux model, I want to we can export the ready-to-solve model. This is quite powerful because once you click on export model and launch Flux2D, the Flux model will appear, and it will be ready to solve. So we can export for the static, the basic model, or the thermal model, and also for the transient. We can export the BackMF model, the scene wave model, and the efficiency map, the model for the efficiency map. We have the FEMP tool inside the Flux that allows you to perform performance mapping. Similarly, is the skew model with less opportunities in this case. And the 3D model, again, we have the basic model without solving scenario, but it's very useful to have it to set up an accurate 3D model. We can also, for the Flux 3D, change the length of the stator and of the rotor, in case, just because if we have, and the magnets, just because if we have some overhang, this can be considered before the export. But let's start with the hyperstudy. That is the tool that allows us to do some optimization on our model. So in this case, we want to perform a working point. We want to perform some analysis and some optimization in the working point scene wave motor, current, control, angle, and speed. So let's go to the second step, that is the test configuration. So for the thermal, we want to have 150. Also, and set the line current density, the line current as 250. The control angle is 37. The speed is 4,000. And yes, we can put yes on the torque ripple because we want to optimize. I mean, our optimization will have the goal, multiple goals. One of these is to reduce the torque ripple. And now we can go to the third step, is the parameters for hyperstudy. I mean, we need to choose the input and the output parameters for the optimization. So first of all, since we want to consider just the magnet geometry, what we can do is clicking on magnet in the section to the left of the screen. And these parameters in blue are available as input. So we need to choose TM1, W1, VM2, VM1, WM1, V1, H1, and TM2. Okay, we have 3, 6, 7 parameters here. We can apply all the inputs. About the output, we can go to the masses and take the magnet masses here, magnet 1 and magnet 2. Okay, as you can see, we can consider the magnet as the total weight of the magnets, or just magnet 1 and magnet 2. I remember you that the magnet 1 is the outer magnet, and magnet 2 are the magnets in the middle of the rotor. So we can also consider the inertia of the rotor, for example, and see how to change, how is changing along the optimization. This data is not useful for our optimization for the moment, but you can use it in system analysis or just know this value for other stuff in the mechanical analysis. So what we need again is the ripple torque. So you can scroll and click on ripple torque here to be able to consider the mechanical torque, the ripple torque peak to peak, and the percentage of the ripple torque against the mechanical torque. So now we have different parameters here. We can apply the inputs and going to the last step. So here we can name the connector the connector. So we can put EPM 80 kilowatts optimization, and you need to set the destination folder, but pay attention since hyperstudy doesn't like long name for the destination folders, so you can receive later some alert, and you can put yes here just to be able to see all the iterations. So apply inputs here. Then we have two possibilities. We can export the connector to use in hyperstudy, or just click on export and launch hyperstudy connector. So clicking on this button, automatically FluxMotor will open hyperstudy with the connector inside. so no further action are needed from our side. Something is taking more time than I expected. Okay. In any case, we have our hyper study is open. Another limitation we have, please, you need to have the same version for hyperstudy and FluxMotor. So hyperstudy 2023 is needed if you have FluxMotor 2023. Okay, by default, hyperstudy is opening, and we can see our model here. As I told you, can couple multiple models. So if you have, for example, a Flux model also, you can just click on Add Model and click on Flux to be able to import the connector. But we have different possibilities. So spreadsheet here, parameterized file like Python script. We can consider a SimLab model. Flow Simulator is the tool that is used behind FluxMotor for the thermal equivalent network. This could be useful in the future when the equivalent network will be available. Other tools that we can use here could be the hyperstudy fit, but is just for more advanced usage of hyperstudy. So this is not the case. But if you are interested in it, it's quite powerful because we can, after performing some analysis, we can reduce our study in a single function and to check the objective, how the parameters can affect the objective in a very, very short time, just using the function. So the first step here is to set up the bounds. By default, FluxMotor uses the shows you the nominal values that we have in the part and suggests the bounds that by default are set to plus or minus 10%, as you can see here. But we need to do some changing to avoid intersection and error in the geometries. So it is quite difficult to do this process since depending on the variation of some parameters, we can find intersection in a very easy way. So what we are doing is to, I mean, it's a process that we need to think before to start the optimization. And to do that, we can open a FluxMotor model to be able to change the parameters. So for example, I can go here, click on edit, and when the motor factory appears, I can go in the rotor magnets and check how these parameters can be changed. So we can change each parameters, click on apply inputs and see if there is some problem in the geometry. Let me just show you a very quick example. If I put 35 here, yes, FluxMotor asked me if I want to continue or not, but we have some constraints in the part. Each part has some constraints for the geometrical point of view. So if we put 35 as the width of the first magnet, in this situation, we will have some problems. So some intersection between lines and so on. So you can check all the parameters here. I already did this step, so we can just set the values. For the lower bound, we have 1.5 for the first parameter. We have 15 for the second one, 2.25 for the third, 0.5 for the magnet for the W1. For the V1, we have 7. The TM2 as 1.5 as lower bound, and the last parameter as 5 millimeters as lower bound. So let's go to the upper bound, 4.5. For the WM1, the upper bound is the same of the nominal value. For the H1 parameter, we have 2.75, it's fine. And in this case, let's try to put 1.5, that is, I mean, a value that is lower than the nominal one. As you can see, we have an alert because the nominal values have to be in the range. So we need to correct this value as, I mean, we need to put the upper bound at least equal to the nominal value. About the V1 parameter, we can put 40, TM2 as maximum value, 3.5, and for the last parameter, we can put 16. Okay, so we changed the bounds for the parameters. We can click on next to test the model and to run, I mean, the model to test if it works fine or not. This is a step that I suggest to do before going into the OE or the optimization, because if you have some problem, here you can see that it appears. If you have some problem, don't hesitate with your workflow. Don't hesitate to write in chat. Normally, the problems could be the solver here that is set by default, because if you install HyperStudy and you already have FluxMotor on your laptop, on your machine, the solvers is automatically added. But if you install FluxMotor and Flux after HyperStudy, you will have to set the solver by hand. Otherwise, you will receive an error here. I can show you just in a minute how to do it. And another problem that you can find is about the length of the path, as I told before. So you need to put the connector, when you export the connector from FluxMotor, in a folder with a quite short path. So we can see that HyperStudy is able to write, execute, and extract the results. So the run is ended, and we can find here the parameters, so the outputs that we choose with the nominal values. So we're starting from a mechanical torque of 195. The torque ripple peak to peak is quite big, and also the percentage is 25, more or less, 24. So the mass is 1 kilo. The total mass is 1 kilo and 70 77. So we can proceed. By default, DOE is suggested. DOE is quite powerful because it allows you to solve multiple combinations between the parameters and to have a matrix of, the results in a matrix that considers all the combination that you set to check the results and see how your project can be improved or not. Okay, so we can go directly to the specification. I hope all of you was able to perform, to test the model. So in the definition, we can, okay, we have the defined models that is the same as before, the defined input variables are different. So we can just, to avoid to repeat the step here, we can just do a right click here and click on add, or view. We can check, we can go to the view and the toolbars to click on approach and study to be able to see the button here. So add, we can add DOE, and the DOE, the definition, can be taken from the setup. Okay, so this time we have the same variables that we already set in the setup, and we can remove the first DOE. Okay, so we have a DOE with the previous bounds. We can avoid probably to run the definition just to avoid to lose time. And we can go directly to the specification. So we have different algorithms that allows you to have an idea of the behavior of the project, of the motor, depending on the variables. And yeah, normally what we can use, what I can suggest to use is the MELS, or the modified extensible lattice sequence, that will take the variables in uniformly distributed mode. So it can, it will take points for the computation quite in a quite uniformly distributed mode, minimizing clamps and empty spaces. So this means that you will have in the matrix that we can perform with the bounds, a quite full matrix. So it will try to take in a reasonable way the points to compute. The second things that I can suggest is the fractional factorial. Here you have the possibility to choose the resolution for the fractional factorial. So by default is 3, and that corresponds to just 8 runs. But you can put 5, for example, to be able to perform 7-4 runs. There is another algorithm that is the sum of the fractional factorial is the full factorial. And you can see a description here. So, but this time, let me choose the modified extensible lattice. Then you are able to change the number of the iteration in this case with the MELS. So you can put 15 or more. It depends on the time that you want to consider, that you want to wait for the results. And then here we can go next. Once we set the specification, we can click on next and going to evaluate into the evaluate stuff. So here we can see the 15 runs that HyperStudy will do, and we can change the concurrent task. So we can use values for the multi-execution that is 8, for example. This for sure depends on your machine. So we can click on next. I mean, here we need to click on evaluate tasks. This will take a lot of time. I mean, in my case, for 15 runs, it will take, it can take 35 minutes more or less. So you can click on evaluate tasks, but I prefer to open the solved model. Okay, let me click on it, then I can stop it just to see how it works. But I want to avoid to wait for this long time, so we'll show you the results, the model that is already solved. And as you can see, we set 8 multi-execution, and the first 8 computation points will started. So we have just to wait that all this table is fit to see the computation. Also, in a few minutes, this bar will suggest you the estimation time of the computation. Okay, some of the runs will fail due to the invalid geometry for some combination of the input parameters, as I told before. Is not a problem, it's fine. I mean, it's expected, so don't worry. For this case, 4 out of the 15 runs failed normally in my test, so no problem. It happens. HyperStudy can just will just ignores the points that will not have results. Okay, so I can stop the sim. I just want to wait for the first results. Stop the computation. Here, then we have other parameters, and we have the purge that allow us to delete all the combinations that HyperStudy runs. It's powerful if you have a quite big model, and so I will create a lot of data on your laptop. In the FluxMotor case, normally this is not needed so much. I mean, the FluxMotor model are quite light, so it doesn't take a lot of memory. We can also create report just clicking on this space here before launch the computation. So these 8 models is running. Okay, what happens if I put the lower and upper bound too far from each other? The values could not be physically possible. Yes, this is what I shown before. So let me give you an example on with the TM1. So outer magnet thickness, as you can see here. If I put 0.5, yeah, this can be very difficult to produce. I mean, if you will ask to produce this magnet, yeah, probably you can receive some segments to position, but it will be very difficult then, because it will this magnet, it will be very fragile. Okay, so the same if I put, for example, 10, for sure I will receive an error here for the intersection. So let me just take the values. Okay, so for example, I can use 8. Okay, also in this case, if I put 8, I think I mean, the supplier can magnetize this type of magnet. Not sure, it really depends on the power that you decide that then to have. But you can find some problems probably then to to find the magnet, or also to manage it. It really depends. Yes, it really depends on the topology you have and so on. So the suggestion here is to decide a priori the bounds that you want to use, just using the part here, and try to differently checking them. By the way, if you put 8 or 0.5, as you see here, the geometry is feasible, but yeah, at the end you will have a not physical results. So this is why I suggest you to decide at the beginning of the process the bounds to use. Okay. Yes, the run inside hyperstudy will fail if we have some intersection. Like, for example, if I put 8, like before, if I put 8. So I suggest you to avoid to leave the predefined bounds, because you can lose time in the hyperstudy computation, because the run can start and then give you an error, and you will have a lot of error then. So you can lose in your, I mean, when you set, oh great, when you set the number of specification, I mean, the number of runs. For example, if you set 2000 number of runs and you will have 120 fails, then you will have and just 18 runs. So it's not what you is not at all what you asked for. To avoid it, you can also add some constraints for sure, and you can do it in the define output response, or you can set. I mean, you can set also not only bounds. Okay, so the first stage is solved. I can stop it. Yes. Okay, as you can see a failure here. That is a failure that I created, that I generated. Is not a failure due to the geometry. But if you found some, or if you encounter some geometric problem in the part due to the bounds that you set, you will have failure here. So the process will continue, but you don't have data for these things. So I don't want to change anything here because we are working. Okay, I can do it probably. Okay, I can, first of all, I can neglect some parameters. Okay, the results are deleted. I can neglect some parameters if I decided then that some parameters has to remain as the nominal equal to the nominal value. So I can just click here And you can see that the parameter will not change along the DOE or during the optimization that we are going to see. And then we can choose different modes to generate the variation of the parameter. It could be normally it is continuous, but we can use a discrete method. And here we can put the lower bound, the nominal bound, and the number of points, for example. So we can set all the data if we want to do heat. We can also check and control the distributions of the points that we are asking for. We can link a variable. This is very useful when you have, for example, a flux model and a FluxMotor model here in Cascade. I suppose that I want to add a flux model here. So then what I will see in the define input variables is that we will have the FluxMotor variables and the flux variables. So in this way, I will be able with the links to link the same variable that we have in the FluxMotor model and the same variable, the correspondent one that we have in the flux model. So it's very powerful. And we can add constraints if you want. Yes, it's a good way to do heat. And we can check it in the library, in the part library. So there is some constraints that the FluxMotor team decided when they built the parametric parts. So also these can be used. So you can add constraints and use some expression and so on. So it's very powerful. But let me close because of the time. No, I don't want to change. I don't want to save. And let me open. Okay, so open. Let me find the right model. Okay, so great. Well, fine. So, oh, why? Let me retry. I probably took the wrong model. Okay. So not sure why I don't have the optimization, but okay. So in our case, the specification was done. So, oh, is this one? But just a moment, sorry. Let's. Okay, so file recent, open. Should be this. Okay, so not results here. I'm so sorry, but I leave you the possibility to check the results. And so let me open the model that we was working on. Is this one? Okay, so in the post-processing, I will show you the results on the let me say on the PowerPoint. Okay, but yeah, I want to show you. I mean, let me take it. Okay, so the most important results for the DOE are the scattered and the Pareto plot, but shows interaction and effect of variable on response. In particular, the Pareto plot is quite powerful because you can choose in the label the values, the output, so the goal that you want to check. So you will have here in the y-axis the peak-to-peak torque, so the ripple torque, and you can see the influence, so the weight of each variable that we choose. And for sure, in this case, we have a big correlation between the age of the magnet respect to the ripple torque. This is quite intuitive. And also we can see the correlation type here, depending on the versus of the lines. The second thing that the second parameter that is affecting the results, so the Coghlan torque ripple, sorry, the ripple torque is the magnet WM2, that is checking the model. This parameter, so the width of the second magnets. Then we have magnet TM2, that is the thickness of the second magnet, is quite intuitive. H1, that is the height of the magnet. The first is the width of the first magnet, sorry. And then we have some two parameters that are just some geometrical, let me say, space in between, that is V1 and W1. V1 and W1. As you've seen, we didn't take all the parameters of the parts, just some of them, because I checked them, and yeah, I think it's enough for our purpose. So about the scatter, we can see in the graph. So we can put the ripple torque average, so in percentage, and the mechanical torque to check how the points, the solutions that we had can be, and to check if we have some points with higher mechanical torque and lower ripple torque that we can choose. So this is an alternative to do the optimization. What is the difference? I mean, the optimization will try to reduce the number of runs depending on the goals that you put and the constraints that you have. So not all the runs will be computed, will be ended. Just the runs that hyperstudy think that can be useful for the optimization. In the case of the DOE, instead, you will have all the points, so all the combination will be carried out. The second scattered graph that is quite important, both for DOE and optimization, is this one that gives you the correlation between the variables. So first variable here is the same here, so we have one as correlation. And here we can see that the ripple torque average as one also with the ripple torque peak to peak because of the same quantity. But we can see also that the average of the ripple torque in percentage is very, very related to the let me say, to the torque. So bigger is the torque, bigger normally could be the percentage. And it is also quite related to the masses of the first magnet only. Yeah. So interesting. You can do a lot of things with these tables for sure. And let's come back to the tool, and let me show you how to do an optimization. So as before, right click here to add a new approach. And this time will be an optimization based on the setup. So we can click on OK. And the defined model is the same. The input variable have the same bounds that we defined in the setup. There is the test model step for sure. And now we have to define the output responses, because before we neglect them. And so we need to add a goal, a constraints for the torque that has to be greater or equal to 193. Since we want to minimize the rotor masses, the magnet masses, I can put here. So rotor magnets here. Minimize, it's fine. And I want to minimize also the ripple torque peak to peak, or the average in percentage is the same. I mean, you can decide when you set an optimization. Then, since we have we defined two goals, the only way is to choose the global response search method that allow us to have multiple goals. You need to set the number of iteration of evaluation. That can be 200 is fine, and apply. So specification is done. You can click on next, and then you can set the multi-execution as before to 8, for example, and evaluate tasks. So the process will start as before, and I will show you the results on my from current slide here. Okay, from my PowerPoints. So here we can see the Pareto front. So you have to choose goal 1. Goal 1 is the magnet mass, and goal 3 is the ripple torque peak to peak. Okay, if you have goal 1 on the x-axis and goal 3 in the y-axis, you will find the Pareto front here. It is a curve that can allow us to choose what is the best compromise between the constraints and the parameters we have, so the combination. We can choose, in our case, a point here or a point here. It depends on your needs. So if we can accept ripple torque peak to peak equal to 35, that is less than the original one, we can take these points, for example, or we can for sure decrease. So then you will find, since we put yes in the FluxMotor process to keep all the iteration, we will have in the hyperstudy connector, we will have in the, let me say, no, let me just open the model. You will find here in the motor catalog all the runs in the folder, in the predefined folder. And so you will find run 1, run 2, and run 3, and just clicking on the, moving the cursor on the points, you are able to see what are the results, and also check the data here, the iteration history, and so on. All the data are available here. Is very intuitive and easy. And we can, at the end, compare the initial design with the optimal design that we have. We can open the optimal design in FluxMotor and check the variation we had in terms of magnet weight, mechanical torque, torque ripple, efficiency, and line voltages. So this was the initial shape, and this is the final shapes, or the optimum one. And we can see we are able also to reduce the magnet, the mass of the magnets. So it's quite good. Okay, so I leave you the way to perform and to the opportunity to check the results and to do the optimization by yourself. We end the training. I hope this training was helpful for you. If you have some doubts, don't hesitate to contact me or to open a new support ticket. Thank you so much for the attention, and have a good rest of the day. Bye-bye.